So far we've only seen slopes of just totally generic graphs, but now let's talk about the slopes of real-life graphs and what they might mean. So to begin with, we often call the slope of a real-life graph the rate of change. So a question might ask you for a slope, it might ask you for a rate of change. They actually mean the same thing. And it's because it measures how quickly or slowly the dependent variable changes, or the y variable, we often call it. So you can see in this graph here that the slope, which is going to tell us the rise, or in this case the fall, over the run, is basically telling us how much time it takes to drop a certain water level. So the slope is telling us how quickly water is draining from whatever this is. So the slope is telling us how quickly something is happening, why we call it also the rate of change. The units of a slope or rate of change are just the units of the rise divided by the units of the run, which makes a lot of sense when we think about it, since the slope itself is just the rise divided by the run. The units of the slope are the units of the rise divided by the units of the run. So let's look at the units for the two slopes in the graphs below. So starting with the one on the left, the units of the rise are feet, and the units of the run are hours. So the units of the slope, so I could say slope units, are just feet over hours. We'd often write this and say this as feet per hour. So similarly, the slope units for the graph on the right are going to be the units of the rise, which is dollars, over the units of the run, which is years. So this is dollars per year. So now let's actually calculate the rate of water draining from this graph that we've seen. So the two things we need to know to calculate the slope are the rise and the run. So we'll start by figuring out the rise, and we can see that because the graph is dropping, it's actually a negative rise or a fall, and it goes from 24 down to 0 feet. So the rise is equal to negative 24 feet. So our slope is going to be negative 24 divided by, and now we need the run. Well, the run begins at 0 and ends at 8, so the run is equal to 8 hours. So negative 24 for rise, run is 8. That gives us a slope of negative 3, and now here's where we have to get the units. Negative 3 feet per hour. So this is telling us the rate that the water level is draining, or water level is changing. Negative 3 feet per hour. For real life graphs, the process might get a little messier because we don't have those perfect grid lines. So we might have to estimate rises and runs. So for example, calculate the rate of change of Canada's population between 1957 and 1987. So first we need a couple of points on the graph, starting with 1957 and going to 1987. And we need to know the rate of change is going to be equal to the rise over the run. So we need to know the rise and we need to know the run. So the rise we're going to have to estimate. It looks like it's going from about, well, we're going to have to estimate, I'm going to say it's about 17 million up to about 27 million. So that would be 27 million minus 17 million is equal to 10 million. The run, on the other hand, is between 1957 and 1987, and we might be able to see that that's 30 years, but we can also do it with subtraction by doing 1987 minus 1957, which gives us 30 years. So the rate is going to be 10 million divided by 30 years. So I'm calculating 333,333 people, because that's the units of the y-axis, per year. So that's the growth rate of Canada, about 300,000 people per year between 1957 and 1987.